Hi there. First of all, thank you to the PWI for giving me this opportunity to speak. To get a presentation ready to give to everybody. So, sustainability, it's been discussed at length in the rail industry for many years. And currently, the UK produces 405 million tonnes of CO2 per year. Globally, we're about 15 gigatons over the target to limit temperatures to a 2 Celsius rise. So there is an awful lot to do. So as a supply chain, why are we doing anything? Well, as we've all heard, Network Rail have committed to being carbon neutral in Scotland by 2045 and by 2050 in the rest of Britain. To waste less, recycle more, slashing the amount of materials they use. So Network Rail have set that challenge. It's up to us as the supply chain to rise to it. But not everything will come from the big headline savings, driving less, flying less, eating less meat. We also need to look at the marginal gains. So the purpose of this presentation is to take a look from a less considered angle and show that by maintaining an optimised track by way of design tamping, Network Rail can cut carbon emissions, provide a safer working environment, and also extend the life of rail assets. So even though rail is the lowest producer of CO2 in transportation, there is always the opportunity to do more. So we can have a look at where we are now. So this is the amount of CO2 released by both passenger trains and freight. This is from the OR Rail Emissions Report 2020-21. So there is almost 2,400 kilotons released from passenger trains and almost 493 kilotons released from freight. That's a massive amount. That is 2,893,000 tonnes of CO2 released into our atmosphere from our trains in a year. We can also, because I'm helpful, we can look at what that compares to. So over 1 billion of your home barbecue propane gas cylinders, or 1.3 million tonnes of coal would produce the same amount of CO2. So 1.3 million tonnes of coal, that is enough to fill Wembley up by 3/4. And if there's any Norwich City fans in here, Wembley's a place where other clubs go to win trophies. So as an example of a marginal gain, if we could reduce the rolling resistance by creating an optimal aligned track through design tamping, it's believed that we could save 5% of fuel. So that would equate to 144, or almost 145,000 tonnes of CO2, 5 million your propane gas canisters, 66,000 tonnes of coal equivalent of CO2 released into the atmosphere. Would also save, so that's also a massive saving of 213 million kilowatt hours of electricity and 32.4 million litres of diesel. I had put £50 million down on here, but I'd guess that's more now because my electric bill's shooting up by quite a bit every day, it seems. So I've already spoken to Darren Sharp. I've completely and utterly stolen your slide from your presentation back in March of this year. But it's a great slide because it shows the CO2 in the assets that are in the track over 1 kilometre. We can see from this that currently over a whole life cycle of a 1,000-metre site, the total embedded carbon is 936,000 kilograms of CO2. So 936 kilograms per metre, 31.2 kilograms per metre per year. And I've highlighted the tamping there because I am going to move on to tamping in a bit. You can see that at the moment there are 10 interventions over the 30-year life cycle. So design tamping using traditional methods can be applied today, but however, the traditional design tamping approach does have disadvantages. It requires staff on or near the track. The survey speed is low. There's limited survey sources available, and a design tamping shift always requires a separate survey shift within a possession. So if they were to go out and survey the entire network, it will be a total of 8,800 survey shifts, and that would equate to 352,000 on-track exposure hours per year. And, you know, do we believe that putting our operatives, our engineers, in harm's way is sustainable? We can also estimate the CO2 from this, and so if the survey teams were to travel to those 8,800 sites per year, say an average of 20 kilometres per site, that'd be 217 tonnes of CO2 per year. And I'd suggest actually I've been quite cautious on the distance, because I know I used to travel all over the place when I was working on the railway. So we can also look at the cost, at how much it costs for renewals and maintenance on the railway, and it's possible to see that Network Rail spend 1.65 billion on renewals and maintenance per year. This does change slightly year on year. So now let's move on to tamping. So what is the difference between design tamping and routine maintenance tamping? As we know, routine maintenance tamping is an essential task to maintain safe track geometry. During maintenance tamping, the tamper machine will collect the data on the current relative track geometry and assess how much the track needs to be moved to bring it back into specification. Put simply, this technique removes short and medium wavelength defects to leave the track in a safe, compliant condition with minimal likelihood of derailment. However, over time and with multiple tamps, use of this technique can compromise the overall track alignment and introduce some undesirable longer wavelength features, produce compound curves and shift transitions, leading to a poor cant build-up. With design tamping, we assess the current track position independently of the actual tampering operation, and then design the optimum track alignment, which takes care of the short, medium, and long wavelength problems. As I've said already, a survey team is sent to site to collect current track position and to then design the track to an optimal position. The optimal position will be input manually into a tamper machine's computer. The tamper will then be sent out to reposition the track to a design position. This is also used on applications such as managed track position, absolute track position, to maintain through alignment design. So let's have a look at the benefits of design tamping over maintenance tamping. Previous studies have identified savings of up to 30% can be made on rail maintenance maintenance budget by moving to a coordinate-based maintenance. Notably, as we see in this chart, a study by the Swiss maintainer SBB found that over a 10-year period, they reduced their maintenance spend by 30%, whilst at the same time improving their track quality by 50%, all while the track load was increasing. So that's surely a dream scenario for a lot of people in here. A similar study by JSC Russian Railways in 2017 found very similar savings on overall maintenance spend and attributed a 10 to 20% saving to design tamping. This makes design tamping the biggest single area of potential maintenance cost savings. This chart displays the types of defects in differing speeds and wavelengths. The literature suggests that design tamping is an effective treatment to eliminate longer wavelengths fault above around 30 metres on line speeds of 100 kilometres, meaning it's a highly suitable technique for vastly more of the rail network than it's currently being used to maintain. And you'll also note on this same chart that the recording cards which record relative track geometry struggle to identify longer wavelength defects. These tend to be the defects which cause vehicle body bounce, which increase the dynamic loading on both the track and the rolling stock, causing them to wear out more quickly. If we can reduce the dynamic loading, this will help to increase the life cycle of both the infrastructure and of the rolling stock. We've already seen how much embodied carbon there are in the assets in the earlier slide, and this will help for large saving. And the other thing is they also cause a rough ride for both passengers and freight. And tools such as Ryder, which I will discuss more shortly, which are based on absolute coordinates, are able to detect features over longer wavelengths than relative track geometry systems, offering the ability to improve the ride quality at higher speeds significantly. So how can we, and I mean we as Fugro now, how can we help make sustainable savings? Well, we've developed a product that, when used for design tamping, will help keep the track in an optimized position. And obviously, when we first came up with this idea, it was to further our ambitions in the rail sector by helping maintenance and tamping managers with their requirements. But as we've developed, we've found that the implications are much more far-reaching, include CO2 reduction, asset life extension, alongside both safety and cost reductions. Investigating the advantages of design tamping over maintenance tamping also led us to be awarded an Innovate UK First of a Kind project by DFT, and our first Smart Tamp project is now ongoing in the Netherlands. So I mentioned Ryder. This is Ryder. It's a system that can be mounted to almost any train, whether it's an in-service passenger train, a loco, or a maintenance train. The system is self-contained and can be connected to a passenger train in less than 2 minutes. The system is autonomous and requires no intervention from the survey or train crew during data collection. So Ryder is a series of tightly integrated subsystems with positioning provided by GNSS, an IMU which tells us exactly where we are on the Earth's surface, producing coordinate-based information. The system at the bottom there has twin railhead laser scanners which image the rail, allowing us to determine the position in X, Y, and Z, from which the geometry can then be calculated. Further, a 360-degree LiDAR scanner records the position of all the assets around the track, such as overhead line equipment, platforms and tunnels, giving us the ability to determine structure gauge. Finally, the system contains 3 high-resolution cameras to produce geo-reference video, which can be used in a variety of applications. So the system's routinely deployed in the UK and in Europe, and in the case of the UK, is approved to provide absolute positional data of rail assets, as documented in Network Rail L2 3100 standard. So I also mentioned Tamp. Tamp was a 9-month project. It concluded back in 31st March 2021. That was a difficult period due to COVID, if everyone remembers that, when the world was at its worst possible state, apparently. But that was great for us. And I'd also like to thank both Jane Austin and Andy Bartlett, who are here from Wales and Western. We actually demonstrated this on their network, and we really needed a committed partner at that time. And boy, did we have one. There's a lot of help, so thank you for that. But note also on this slide that I've highlighted the word demonstrate, and this was a contractual obligation. The Tamp process was intended to be a practical application which can be implemented rather than just blue sky principles or base principle research. So let's look at Smart Tamp now, which was born from this project. So Smart Tamp is a modified approach to design tamping. Smart Tamp focuses on applying the collected geodetic data to create an optimized safe track alignment. Geodetic reference data is post-processed to supply a 3D laser point cloud and data relating to an absolute track position. This is then used to model the optimum alignment whilst maintaining gauge clearance to structures and the appropriate heights and stagger for OLE. In conventional maintenance tamping, the lift and slew of the track is restricted to 40mm and 25mm, respectively, from the original design position. To avoid any potential clash between rolling stock and corridor infrastructure, by modelling the track in 3D space in relation to surrounding assets, it's possible to design the new track alignment with confidence beyond the previous 25mm limit to achieve the optimum alignment for the smoothest ride. Once finalised, the design alignment is converted into the corresponding track adjustments, lifts and slews, and can be input into the tamping equipment. The surface profile can be used to accurately determine the current ballast volumes and the tonnage of ballast needed to bring the ballast profile into line, providing exact locations of where to drop the ballast to achieve the designed track lift. Smart Tamp is a comprehensive solution that offers more sustainable whole life geometry and increased track quality, which will ultimately reduce maintenance costs and improve safety. So here we can see the benefits of using Smart Tamp. So let's take a deep look into that. So earlier we said that surveys across the whole network would equate to 352,000 exposure hours per year. Well, with Ryler, the Ryler crew's only on the track at the start of the shift and at the end of the shift. And that's 2 minutes to attach Ryler to a train, 2 minutes to adjust. Oh, sorry, you'll also notice this was done in Holland, by the way, so they don't have to wear orange trousers, but just to keep it in our standard, I coloured it in for everyone there. And that was about 20 minutes on a Sunday, which I will never get back, but anyway. So 2 minutes to attach, 2 minutes to detach. Therefore, Ryler survey reduces boots on ballast by 97%, which is a reduction of 339,500 on-track exposure hours. And currently, as I've said, a design tamping shift always requires a separate survey shift, and this shift can be eliminated by the use of Smart Tamp. So, however, currently for compensation tamping, time is also lost on the shift as the tamper itself needs to survey the track during the night. The tamping work will be executed. So if we assume in a night the tamping machine is effectively 4 hours at the project location, the first hour is needed to do the survey, set back, calculate and approve the compensation lifts and slews which are to be applied. So this reduces the amount of time available for tamping by 25%. By having the full amount of time to complete a tamping shift, the tamper will be able to complete 25% more per night. So the opportunity to improve the efficiency of tamping machines therefore arises at locations where compensation tamping is currently applied. The information provided by Ryler surveys can be directly input into the tamper's machines, and they will not have to execute a measurement run anymore, only a short calibration run. The only condition for this approach is a design or alignment along with Ryler data must be readily available. So currently, Network Rail executes compensation tamping on average every 5 years, so a scope of 3,500 kilometres per year for compensation tamping. The costs for a tamping shift are approximately £8,000. And so if a tamper can tamp 975 metres per shift, and if I'm quite happy to be challenged on that 975 metres as an average, but I got it from the OOR report on machines, and that was the average across all of the routes and regions. So if it could do 975 metres, price per metre is £8.21. With the 25% extra, you're able to carry out that much more, so it brings the price per metre down to £6.51. That's a saving per metre of £2.06. So, of course, being BD, I'll put that across the whole network. That's a saving of £66 million across the whole network. Again, jump back to Darren Sharp's fantastic slides. And as you remember, we're currently 31.20 kilograms of CO2 per metre per year. With Smart Tamp, you can notice, I think the first thing most people notice is actually we've increased the asset life now by 20%. So it's an increase of 6 years to that asset. Also, we actually only need, because the rail is in a better, more optimal position, there's less wear and tear, we only need to carry out 9 tamping interventions over a longer period. So this drops the total CO2 down to 927,700. Actually, I've messed up this slide. It should be 928. But anyway, so that's 928 kilograms per metre. That's 25.77 kilograms per metre per year. So if we were to put, we were to put that saving over the entire rail network, that's a saving of 173,760 tonnes of CO2 per year. Over 6.5 million of the gas calendars and 79,000 tonnes coal equivalent being released into the atmosphere per year. So if we were to move on to the cost reductions, and as you remember, I said it was 1.65 billion is currently spent. If we were to take the 30% cost reduction, then that would be a saving of £495 million on maintenance per year. And design tamping contributes to 66% of that, which is a saving of £330 million per year. I will, of course, add caution to these massive figures, as these are for the whole network. And so this would take a gradual rollout to make across the main routes first before we tackle the other areas of the network. And to be open, we also haven't allowed for the cost of one-off designs, but it won't be anywhere near that figure of 495 million. So, all of the carbon savings that I've discussed so far. So this comes to almost 319,000 tonnes. And of course, I had to throw in my, my flow gas propane cylinders into there. So 11.5 million of those and 145,000 tonnes of coal. And now we can have a look at the comparisons of maintenance tamping, design tamping and smart tamp. As you can see, all three are safe and compliant methods of tamping the rail. But with design tamping and smart tamp, you have a 20% increased lifetime of assets, 5% fuel reduction, 30% cost reduction, and increased tamper utilisation. But sorry, this slide's gone a little bit funny in the wash there. But smart tamp goes a bit further. We also offer 97% boots off ballast, reduced survey CO2, ballast management. Our design data is available for other operations. Our mantra is survey once, use many times. And we also offer regular infrastructure monitoring. So just to wrap up, the annual savings that we believe smart tamp can bring to the entire network, almost 319,000 tonnes of CO2 saved per year, 339,500 hours of on-track exposure hours saved per year, and upwards of £500 million per year. So, yeah, I hope this presentation has been useful. I hope it sparked some interest in our products, and if anyone would like to speak to me, I'm more than happy to show a demo. But more than anything, I hope this has shown that we can actively change the way we look at sustainability. We don't have to go back to the drawing board and start again. We can use what we already have, but in a more optimised manner, and produce an even more sustainable railway for the future. Thank you.